relationship to eigenvalues. Now, I will explain. You don't have to know too much about eigenvalues. You must have heard about it, at some point if you're taking differential equations or matrix algebra. Going back to the characteristic polynomial, we have 1 minus v1z minus v2z squared, and we are setting that equal to 0.
Just double check this is no longer complex, just backing off.
We're going back to simply the characteristic polynomial. What do we mean? Well, let me ask you this. Always like to connect something to simple so we can understand. I want you to write that in a factor form. X squared plus 3x plus 2. The factor form for x squared plus 3x plus 2 is simply x plus 1 times x plus 2. Here is the question. If I want to solve for the root of x squared plus 3x plus 2, it is equivalent to saying I set each of these factors equal to 0, right, from algebra. So every polynomial can be expressed in terms of factors. A second-degree polynomial stochastic quadratic function can be expressed, using 2 factors, cubic, 3 factors, quartic, 4 factors, and so forth. So instead of, writing it this way, I'm going to say, well, I know I can rewrite this as a factored version, so why not call it as 1 minus lambda 1 z multiplied by 1 minus lambda 2 z. I'm simply using z because that's what I have here. I want to set each factor equal to 0. But do keep in mind, they can't be the same value of z. Do you agree? I left it as z because where does z come from? It comes from the lag operator. I replaced the operator by the letter z. But we know we need to have 2 different roots, z1, z2. So if I set that equal to 0, I will end up getting lambda 1, which is simply the inverse of z1. Good. Just for the purpose of finding the solution, So if we want to find lambda 1, we're just inverting z1, lambda 2, we're inverting z2. Going back to the factored form of the characteristic polynomial, which is simply 1 minus lambda 1 z multiplied by 1 minus lambda 2 z. The slight point of confusion that students often have is from here to there. I've only used z here, but when I got to there, I called it as z1 and z2. This is something we've done it in algebra also. You have a quadratic equation in terms of xy, like the one I wrote xy plus 3x plus 2 equals 0. You find two roots, one is -1, the other is -2. Those are the two possible solutions. I'm just going to call that as x1, call that as x2. Right? Even though we had just one x, we have two roots, same argument. Now, if I pull z out of this, I'm pulling a z out. Z comes out, z comes out. And that is going to result in 1 over z minus lambda 1 multiplied by 1 over z minus lambda 2 equals 0. I'm going to divide out the z's square. So have z times z square. And I'm simply going to call 1 over z as just lambda. So I'm going to get two distinct lambdas when I solve this equation. Of course, lambda 1 and lambda 2 will in turn depend on phi 1 and phi 2. We don't want to get into that part.
So you just made one over z just into a lambda.
Yes. So lambda is just 1 over z. That is correct. Now, how does this relate to an eigenvalue? The book uses F. So we want to consider the matrix F. F is simply phi 1, phi 2, 1, 0. That's the structure. It doesn't change. If it is a third order difference equation, it will have a structure. I'll explain it when the time comes. When I derive that stuff. So all we have to do here is to find the eigenvalues of F. If you don't know this process, that's okay. We want to find the values of lambda such that f minus I lambda is equal to 0. What is I? I is what we call the identity matrix. If you multiply any matrix by the identity matrix, you end up getting the same matrix, which is why we call it the identity. So that's what I'll end up having. Good. Which is the same as saying phi1, phi2, 1, 0. If you have a number, which is just lambda, multiplied to the identity matrix, it will become lambda 0, 0 lambda. These are just properties of an identity, matrices of any matrix. If it is addition or subtraction, we can just combine the elements directly. But matrix multiplication, you have to go through that process that I explained last time. So this would be phi1 minus lambda, phi2, 1, and phi2 minus lambda.
With this, are we using this as like an arbitrary lambda, not like the 1 over z that you had earlier?
Come again.
This is like an arbitrary lambda, not like the 1 over z.
I'm trying to make the connection. Good.
Wait, hold on. Wouldn't the bottom line just be 0 minus lambda?
Ah, thank you. That just was looking funky. So I have this matrix, I'm going to set that equal to 0, because that's how I'm going to find the eigenvalues. We need to find the determinant of this matrix. So determinant of any matrix A, if I define A to be A, B, C, D, always equal to AB minus BC. For bigger matrices, we have to go through this process of finding the determinant, but for now, this is all we need. So A in this case is phi1 minus lambda. Multiplied by negative lambda. Over there, it's just negative phi2. Good. So distribute, you have lambda squared minus phi1 lambda minus phi2 equals 0. Good. That, once again, the right-hand side, in matrix algebra and in differential equations, is called the characteristic polynomial. Now you know where that, where it comes from, or the phrase characteristic polynomial comes from. My argument is finding the eigenvalues of that matrix is the same as finding the roots Z1, Z2. How? I called lambda to be 1 over Z. So I'll have 1 over Z squared minus V1 multiplied by 1 over Z minus V2 equals 0. Good. Multiply by Z squared on both sides. What happens when you distribute that Z squared?
You get 1.
Z squared, 1 minus phi1 multiplied by 1 over Z multiplied by Z squared will give me phi1 times Z. Negative phi2 Z squared. Good. So I want you to look at this, and I want you to look at the characteristic polynomial that we started with at the beginning of class.
Same thing.
They are one and the same. So just like a regular quadratic polynomial, if I have two roots, I'm going to call it lambda 1, lambda 2. And initially I set lambda to be 1 over Z. So if I find the eigenvalues of that matrix, invert those eigenvalues, I'm going to get the roots. You may ask me, well, who the hell cares? That characteristic polynomial is easier to solve if we simply have order 2, right? If it is order 3, then that would become a problem because you want to solve a cubic polynomial. That's not easy. And imagine if you want to solve a fourth order polynomial or characteristic polynomial like we had in the homework. Those would get complicated, but finding eigenvalues are always easy. Finding eigenvalues would simply mean you form that matrix and then go to your calculator, hit eigen, you will get lambda 1, lambda 2, lambda 3, lambda 4. You could get any number of lambdas. So you could have a 10th order difference equation where whatever you measure today is dependent on the last 10 days. And if you have that 10th order difference equation, I'll have a 10th order polynomial, but solving that is going to be a piece of cake because I know for that 10th order polynomial, all I have to do is come up with the matrix F. And if I find the eigenvalues of the matrix F, I can invert each of them to find the roots. Does that make sense? So next time, I am going to pick a simple second order difference equation and do an example where we're going to find the roots, Z1, Z2, hopefully not complex. And then we are going to use the eigenvalues to see that we end up getting the same answer. Once we're done with that, there is one more approach where we find a solution And that should do for now. Then we can move on to chapter 3 and come back and visit the p-order difference equation. I want you guys to get comfortable with the first and second before we go to order 3.